Welcome to the deep dive. So you've probably heard about Gödel's incompleteness theorem, right? It pops up a lot in popular science.
Oh, yeah, definitely. Often with some pretty dramatic interpretations.
Exactly. Like you hear Neil deGrasse Tyson saying, at some point in mathematics, you just have to make something up.
Hmm.
Or Deepak Chopra connecting it to consciousness, saying it shows the limitations of almost every theory of reality.
Right. And Veritasium's hole at the bottom of math idea that we'll never know everything with certainty.
Big claims, they sound huge, but, maybe a bit misleading.
That's often the case, isn't it? These ideas are complex, and the popular versions can drift quite a bit from the actual, the technical meaning.
Okay, so that's exactly what we want to do today. Let's try and cut through some of that hype.
Good player.
We're going to dig into what Gödel's theorem really says, using insights from Curt Jaimungal's work on his channel. He's done a great job clarifying this stuff.
He really has. His explanations are quite clear.
And here's the main thing right up front. Gödel's theorem. It's about axiomatization, specifically limitations within formal math systems.
Precisely. It's not some grand statement about everything we can possibly know, about epistemology in general.
Right, epistemology being like the study of knowledge itself, what we know, how we know it. Much broader.
Exactly. Gödel's work is super specific to these formal logical systems, proof, deduction, all within very clearly defined rules.
Okay, so let's get into it. What did Gödel actually prove?
Hmm.
The first incompleteness theorem, what's the core idea there?
Well, basically it says this. Take any formal system, one that's consistent, so no contradictions, and also mechanically checkable, recursive. If that system is complex enough to do basic arithmetic, then there will always be statements about arithmetic that are true, but that the system itself just can't prove, or disprove, for that matter.
So it's not just that we're missing the proof, it's fundamentally unprovable within that system's rules.
That's it, exactly. And the really clever part is Gödel didn't just say these statements exist, he showed how to actually construct them.
Wow.
Yeah, so it wasn't just theoretical. He gave a method. It means any consistent system strong enough for arithmetic has, an inherent blind spot.
Jaimungal uses this analogy of a hard ceiling for a proof system. What does that mean?
Think of the system like a machine, okay? It takes axioms, the starting assumptions and rules, and it cranks out proofs.
Right.
Gödel showed that for any such machine doing arithmetic, there are truths it just can't reach. It hits a ceiling.
But we're not stuck under that ceiling forever.
Well, no. As Jaimungal and Scott Aronson point out, you can always zoom out. You can add new axioms, make the system stronger, build a, taller machine.
Yeah, so you beacon up.
Right. But
Yeah.
then Gödel's theorem applies again to that new, bigger system. It will have its own ceiling, its own undecidable truths. It kind of goes on forever.
Huh. Okay, that's a helpful picture. And you mentioned two conditions earlier, consistent and recursive axiomatization. Why are they so crucial?
Consistency is, fundamental. If your system proves something and it's opposite, it's useless, right? It tells you nothing reliable.
Absolutely. Total chaos.
And recursive axiomatization, that just means there's a definite procedure, like a computer algorithm, that can check if any given statement is one of the starting axioms or not.
Mechanically checkable.
Exactly. That's vital because Gödel's proof kind of involves the system talking about itself, which needs that formal precision.
Got it. So we have this theorem about limits inside formal arithmetic systems. Now let's tackle those popular interpretations again. Why are they often misleading? Jaimungal calls it a category error.
Yeah, that's a great way to put it. The error is taking this very specific result about formal math and applying it to completely different categories, things like consciousness or reality in some vague sense, or all of human knowledge.
It's like comparing apples and oranges.
Totally. It's like using, a theorem about prime numbers to explain why your car won't start. The logic just doesn't transfer. These theorems about formal systems don't automatically become rules for, metaphysics or consciousness.
Okay, let's look at Neil deGrasse Tyson's quote again. At some point in mathematics, you just have to make something up. How does that connect, or rather misconnect?
Well, as Jaimungal points out, that sounds a lot more like he's talking about axioms themselves.
The starting points.
Exactly. Axioms are assumptions, things we start with. Gödel's theorem isn't saying we need to randomly make stuff up because of incompleteness. It's saying even with a clear set of axioms, there are limits to what you can derive from them.
And axioms aren't usually just plucked out of thin air.
Not at all. Bertrand Russell talked about this. You often justify axioms by looking at the consequences, seeing if they build a useful, consistent system. They aren't just arbitrary guesses.
Okay. What about Deepak Chopra, linking Gödel to consciousness and the limits of reality?
That's really stretching it, you know? Gödel's proof is strictly about arithmetic within formal systems. It says nothing, absolutely nothing, about consciousness or some grand theory of reality.
So pulling in consciousness is just unrelated.
Completely. I mean, you hear Gregory Chaitin's phrase, truth outruns proof, which is related, but Chaitin himself meant that within mathematics.
Ah, okay.
It's not a license to just throw mathematical concepts at any philosophical idea. Jaimungal even mentioned canceling an interview because someone was misusing quantum physics concepts alongside Gödel, which kind of shows how easily these things get tangled up incorrectly.
Right. And then Veritasium's hole at the bottom of math, meaning we can't know everything with certainty.
That's another subtle misreading. Gödel shows a limit within a single formal system. It can't be both complete, prove all its truths, and consistent.
But that doesn't mean we humans are limited in the same way.
Exactly. We use multiple systems, we use intuition, observation, creativity. The whole is in that specific logical structure, not necessarily in, like, the entire human capacity for knowledge.
So the takeaway isn't that math is broken or unreliable.
Definitely not. Math is incredibly powerful and consistent in practice. Gödel just puts a boundary on what any single fixed set of axioms can achieve when trying to capture all of arithmetic truth.
Okay. Now, Jaimungal brings up some important nuances. Like, there isn't just one incompleteness theorem.
That's right. There are two. The second one is maybe even more profound for foundational questions.
What does the second one say, roughly?
It says that a consistent system powerful enough for arithmetic cannot prove its own consistency.
Whoa. So the system can't even verify that it's non-contradictory using its own tools.
Exactly. That was a big blow to the hope of finding a single, self-contained, provably consistent foundation for all of mathematics.
He also mentions Roger Penrose's ideas connecting Gödel and consciousness. That sounds like a whole other deep dive.
Oh, it is. Penrose argues that because we humans can see the truth of certain Gödel sentences that are unprovable within a system, our minds must operate beyond purely algorithmic computation.
So consciousness has some non-computable element.
That's his argument. It's fascinating, but very controversial. Definitely something to explore separately, as Jaimungal suggested.
Another point Jaimungal raises is interesting. We don't usually use axioms to justify our basic math understanding, do we?
No, it's usually the other way around, isn't it? Our intuition about numbers, about basic adding and subtracting comes first.
From experience, maybe.
Yeah, experience, intuition. Then we build axiomatic systems later to make things rigorous, to explore deeper. Russell had that analogy using axioms to justify basic arithmetic is like building scaffolding to hold up the ground, kind of backward.
Yeah. And I also mentioned more mundane limits on knowing all of math, which I liked. It's not all about Gödel.
Absolutely. Just think about our own limitations. Finite memory, finite processing speed, finite lifespan.
Right.
Forget Gödel's theorem for a second. Try adding two numbers with, like, a googolplex digits each. It's practically impossible for us, even though the arithmetic itself is simple. There are very real physical constraints.
Okay, let's go back to those undecidable truths Gödel guarantees exist. Jaimungal says they aren't globally true, but model-dependent. What's that about?
Okay, this is a bit subtle, but important. It connects to Gödel's other major theorem, the completeness theorem.
Not incompleteness, but completeness.
Right. That one says if a statement is true in every possible interpretation, every model of a formal system, then the system can prove it.
So if it's universally true across all models, it's provable.
Exactly. Therefore, the statements that the incompleteness theorem says are unprovable, well, they can't be true in all possible models.
Ah, I see. So they must be true in some models and false in others.
Precisely. We usually think of them as true in the standard model of arithmetic, the one we all intuitively use. But you could, in theory, construct weird, non-standard models where those statements are false. So their truth isn't absolute across every conceivable mathematical reality.
That is subtle. Okay, so what if we just find one of these unprovable but true in the standard model sentences and just add it as a new axiom? Problem solved.
Nice try. But nope, doesn't work.
Why not?
Because, as Jaimungal explains, you just create a new, slightly stronger formal system. And assuming it's still consistent and checkable.
Gödel theorem applies again.
You got it. The new system will have its own undecidable sentence. You can keep doing this, adding the unprovable sentence as an axiom, but you just climb up a ladder where each rung is still incomplete. It goes on ad infinitum.
Wow, okay. No easy fix. Interestingly, Gregory Chaitin apparently sees this whole thing not as a downer, but as freeing.
Yeah, that's a really different perspective. Chaitin, who worked a lot on randomness in math, kind of sees incompleteness as proof that mathematics isn't this closed, static thing where everything is eventually derivable.
But more like open-ended,
Yep.
creative.
Exactly. An open system full of surprises where truth can actually outrun formal proof. It suggests math is more dynamic than maybe people thought before Gödel.
Cool perspective.
Yeah.
Now, Jaimungal mentioned an important asterisk connecting us to computable proof engines and epistemology. What's the link there?
Well, think about computer programs that check mathematical proofs. They're everywhere now.
Right, proof assistance.
Essentially, any such computable proof engine is an implementation of some formal axiom system.
Okay.
So, Gödel's theorem directly applies. It puts objective limits on what any algorithm, any computer program can certify as true based on a given set of axioms.
And how does that loop back to epistemology, to how we know things?
Because we increasingly rely on these engines, right? We trust them to verify complex proofs we couldn't possibly check by hand.
Yeah.
So the limitations of these formal systems, these engines, become relevant to the scope of our verified knowledge.
He gave the Peirce-Harrington theorem as an example. How does that fit?
Right, that's a great example. It's a statement about numbers, specifically combinatorics, that is known to be true. We can prove it using stronger mathematical tools.
Okay.
But it's been proven that you cannot prove the Peirce-Harrington theorem using only the standard axioms of Peano arithmetic, a common system for basic arithmetic.
So Peano arithmetic hits its ceiling with that theorem.
Exactly. It's true. We know it's true. We can prove it's true using other accepted math, but it's beyond the reach of that specific foundational system. It clearly shows we can know truths that are unprovable within a particular formal framework.
It really highlights the limits of the system, not necessarily our knowledge overall.
Precisely.
Sounds like Gödel's theorem gets misused quite a bit outside of math and logic, too.
Oh, definitely. Jaimungal mentions theologians trying to draw analogies between Gödelian limits and knowing God.
Which is?
A classic category error, as he says. Applying math logic to theology just doesn't track.
And philosophers, too.
Yeah, some continental philosophers have apparently tried to use it to argue for radical indeterminacy or undecidability in their own, often quite vague theories. Again, it's taking a very precise mathematical result way out of context.
Misapplying the tool.
Totally.
He also touched on partial knowledge and how Gödel's proof relies on infinity, in a sense.
Yes, the proof technique, the Gödel numbering, requires the system to be able to handle arithmetic with potentially unbounded numbers. It needs to encompass essentially all of elementary arithmetic, which includes the idea of arbitrarily large integers.
So if math was strictly finite, like numbers only went up to 1 billion,
then the standard incompleteness arguments wouldn't apply in the same way. The possibility of infinitely large constructions is kind of baked into the proof.
And he also said, even if our minds were formal systems, we're probably not consistent anyway.
Yeah, that's a good point. Gödel assumes the system is consistent. Human belief systems. Well, let's just say we often hold contradictory beliefs simultaneously, so that key assumption might not even hold for us.
Good point. So if we boil it down, what's the big picture takeaway Jaimungal emphasizes about axiomatization versus knowledge?
I think it's that setting up axioms, creating a formal system, doesn't automatically capture all knowledge in that area. Axiomatization isn't the same thing as complete knowledge. This was maybe hinted at even before Gödel, with things like the Lowenheim-Skolem theorems.
Right. And it's just so important to remember the specifics here. Gödel's theorem has assumptions.
Crucial assumptions. Consistency, recursive axiomatization, ability to express arithmetic. It's powerful, but specific.
And applying it outside that context, especially to broad epistemological claims, needs extreme care.
Exactly. And related ideas, like whether the human mind is a computer subject to these limits, the Church-Turing thesis, applied to the mind, that's still a really open and debated question itself. You can't just leap from Gödel to conclusions about the human mind without tackling all that complexity.
Okay, so let's try to wrap this up. Summarizing our deep dive, what's the core distinction you want people to leave with about Gödel's incompleteness theorem?
The key thing is, it's a profound result about formal mathematical systems, specifically their ability to prove truths about arithmetic within their own framework.
But it's not an automatic universal limit on all human knowledge.
Precisely. It doesn't just scale up to become a general law of epistemology limiting everything we can ever know. That's the category error we talked about.
Still, even if it doesn't support those really grand, sweeping claims, it does tell us something deep, right? About formal systems themselves.
Absolutely. It shows an inherent boundary within any sufficiently complex, consistent formal system dealing with arithmetic. There will always be truths within its domain that lie beyond its ability to prove. An intrinsic incompleteness.
That's a much clearer picture, I think, than the usual sound bites. And it makes you think, doesn't it? About how else we know things. Intuition, seeing patterns, observation, creativity.
Right. Maybe the limits Gödel found tell us more about the nature and limitations of formal proof as a way of knowing, rather than some absolute limit on knowledge itself.
A really fascinating thought to end on. Definitely encourages you to think about different kinds of knowledge. We'll put links in the description to Curt Jaimungal's channel, our previous deep dive on Getting Your Problems with Jennifer Nagel, and that Substack post Jaimungal wrote, if you want to explore these ideas more.
Sounds good. Lots to think about there.
For sure. Thanks for joining us for this deep dive.